today can still see what the presentation is about. So to celebrate World Wetlands Day, first of all, we have Shachi Bahl from India, who's presenting her work on urban freshwater wetlands in Christchurch. Shachi's been working on her project with us for 3 years now, and so it's starting to come together for her PhD project. And after Shachi's finished speaking, we'll move straight on to Charlotte Calder, who's now working for Rough, Milne and Mitchell down at Wanaka, in their Wanaka office. And she's going to tell us a bit about her master's project that focused on riparian planting design for her family's farm down in central Otago. After Charlotte's finished, then we'll open up the floor for questions, if anybody has any comments or questions for the two speakers. If you'd like to ask your questions either in the chat room or the chat box to the right of your screen, or if you want to open up your mic and ask questions through the mic, that would be fine. So Shachi, if you could get started, that would be great. Thank you.
Thank you, Jill. Hello, everyone. I'm Shachi, and my PhD project is about optimizing carbon storage potential through design of urban freshwater wetlands in Christchurch. I'm supported by Dr. Gillian Lawson and Dr. Nada Toueir as my and Dr. Antony Shadbolt as my supervisors for this project. I am very grateful to them for the support and the constant guidance that they have provided, which has made this project reach at this stage. I am today I'm going to share about some of the findings that I have come across that reveal the patterns for carbon storage in freshwater inland wetlands specific to Christchurch. And I'll be sharing these findings with you in this presentation. Starting with a brief introduction about wetlands and their importance in the global carbon cycle around the world. So they are considered important for carbon cycling because they represent almost 15% of the terrestrial organic matter losses to the oceans, and which makes them significant carbon sinks. They cover less surface area, but they account for almost 30% of world's soil organic carbon pool. And so they are responsible. They are very efficient ecosystems for storing organic carbon in the soils. And amongst all the terrestrial ecosystems, they are known for having the highest carbon density, and which makes them have a high contributing value as a climate regulating service in the world. So carbon sequestration is an important ecosystem service which is provided by wetlands around the world. So looking at this is a publication from a study done by Villa and Burnell in 2018, where they are comparing carbon stocks in different types of wetlands, and they made this comparison with tropical forests as well. So what I found from from their findings is that they combined the data for all temperate and tropical freshwater wetlands, and I found that the soil carbon storage was highest when compared to other kinds of wetlands around the world, which include mangrove swamps or coastal wetlands and northern peatlands. And then when I made a look into the amount of investigation that has gone into freshwater wetlands, what I found was that out of 110 independent studies carried out by the same authors, carbon sequestration was widely studied for coastal wetlands, which made up almost 53% of the entire of their study. Then Non-forested peatlands made up to 14.3%, and there was very little importance given to freshwater wetlands. So looking at the data that where freshwater wetlands can store large amount of soil carbon, and there was very little, and especially temperate freshwater wetlands, they have a very high caliber for storing this carbon. And looking at the fact that we don't have enough studies for to create enough data or evidence to give importance to these wetlands. This motivated me to study these ecosystems in Christchurch. And so I started investigating freshwater wetlands and their soil carbon stocks in Christchurch. And what I found from my studies is that soil carbon stocks is a function of three main factors in these wetlands. The first is vegetation, which combines the dominant plant communities at these wetlands and the assemblages, the way these plant species are planted in the wetlands. The second are the water levels, which include the water and sediment flow and their retention time within these wetlands. And the third are the soil types, which could either be peat, considering the temperate climate in Christchurch, or mineral soil types, and the amount of nutrient availability in these soils, which influences the plant biomass and carbon storage in these wetlands. And so the interaction between these three, vegetation, water levels, and soils, creates a signature characteristics of these ecosystems, which is also then used to differentiate and classify wetland systems. So all these processes I am looking at within the wetland scale of my selected sites. And all these processes in turn affect plant community structure, redox potential, and soil carbon storage in their biomass. So studies have shown that freshwater wetlands provide a potential sink for atmospheric carbon, but if they are not designed and managed properly, they could become sources of greenhouse gases such as carbon dioxide and methane. In my project, I'm looking at ways in which we can improve these carbon stocks, and I'm focusing only on sequestering of carbon in these wetlands, and there is less emphasis on the release of carbon into the atmosphere, because what I found from my study is that although wetlands are considered to be both sinks and sources of carbon, within a if we design them properly, within a 300-year period, their ability to sequester carbon far exceeds their ability to release carbon back in the atmosphere. So I am looking at design consideration of these plant communities and plant structures in these wetlands that could help improve storage of carbon, both in the above ground biomass as well as in the below ground biomass of these systems. So the research gap, I came across two research gaps from the literature. The first one is a lack of understanding of the plant-soil interactions that are responsible for regulating soil carbon cycling in the wetlands. What I mean by this is that despite the known importance of soils and for their role in carbon cycling, surprisingly, very little is known about the factors that regulate the fluxes of carbon to and from the soil, or from the role that interactions between plants and soil biota play in regulating soil carbon cycling. So there is enough evidence which says that soils store carbon, but there is not enough evidence which explains the mechanisms which govern the processes that influence these interactions between plants and soils. And second, there is a significant information on the influence of plant diversity on the ecosystem productivity of the systems, but little is known about the correlation between structural diversity and the mechanisms that return carbon to the soil. So one of the reasons is the technical difficulty which researchers face during while they are assessing carbon storage in various ecosystems, making these correlations. So how I'm aiming to address these research gaps are, first, to understand the relation between plant species and carbon sequestration in the selected sites of my project. Second, I want to identify key sites of carbon sinks and the role structural diversity of plant assemblages plays in influencing the carbon storage in these areas. And third, I want to determine design considerations for these plant assemblages that would collectively support in optimizing carbon sequestration capacity of freshwater wetlands. And I'm specifically focusing in Christchurch as my study area. Presently, I'm in the analysis and determining the research implications for my project. It's a very intensive work, and I'll be showing you the processes that have gone into generating the data sets required for analyzing for a project like this. So today I'll be only able to share with you the findings that I have come across in my project, which explain, which show the patterns and the trends of carbon storage at 2 of my sites. So typically, freshwater wetlands are known for storing carbons in 6 reservoirs. They are plant biomass carbon, soil carbon, third is microbial biomass carbon, fourth is POC or particulate organic carbon in the water column, fifth is dissolved organic carbon, and sixth is gaseous carbon compounds such as carbon dioxide and methane. Out of these 6 reservoirs, I am looking at 2 of them in my project, which is plant biomass carbon and soil carbon, because I feel that these 2 are enough to give evidence about the plant-soil interactions that are responsible for carbon storage at the wetlands. And they would be enough to generate the data based on which we can come up with research implications for how we need to design these assemblages, or how we need to spatially arrange these plant communities in freshwater urban wetlands in Christchurch. So the map shows different types of wetlands in Christchurch, and out of this I have selected a freshwater wetland on the east and near the east coast of the city, which is Travis Wetland. And the second, Travis is a restored site, and the second is Sparks Wetland in the Halswell catchment. In the Heathcote River catchment. It's a newly constructed wetland in Christchurch. Travis Wetland was established around 24 years old, and it is a very good example of a restored site, a restored freshwater wetland site in the city. And Sparks is a newly constructed wetland meant for filtering storm water from the surrounding catchment. And so both of these are freshwater systems, and I wanted to investigate the plant communities in both these systems to understand the dynamics that that create certain conditions in the soil for enhancing the carbon storage in their domain. So up to this stage, we have identified 7 dominant plant communities at Travis. First one is the paddocks, and there are 4 different types of paddocks at Travis. Second are the sedges, 3 different types of sedges. Third wetland plant community are the reeds. Fourth is the native forest species. There are 4 different kinds of native forest species. Fifth are the coastal bush species along the sand dune area. Sixth are the native plants that are used along the water margins. And seventh are the willow forests, 2 different types of willow forests that are existing at the site. And together they form the vegetation community plan for wetland, which was observed within the years 2020 to 2021. Similarly, for Sparks, 5 communities have been identified. The first one are the rushes. Second are the sedge communities. Third are few forest species along the boundary. Fifth are the native shrub plantings, and the sixth one is the pasture grass, which are together culminating in creating a vegetation vegetation plan for Sparks wetland. And when we look at these two, the vegetation plans for these two wetlands, there are a lot of similarities in terms of the dominant plant communities that have been planted here, especially in the terms of the pasture grasses or paddocks, or the native plant communities along water margins, the sedges and the rushes. And there are, with the exception of native forest species, the planting is quite similar in both these wetlands. The reason, just a reminder that Travis is a restored site and Sparks is a newly constructed wetland. And when I looked at the soil carbon, when I looked at the soil carbon density, which is soil carbon concentration per meter square at both these wetlands, I found similar patterns. So the mean soil carbon density values were greater for wetland plant community, the second one, which is the sedge and the rush species, and this was followed by this was followed by the willow swamp forest species. And the reason that these two plant communities, the sedges and the willow forest, had high carbon concentration values can be the reason is the soil type and the water saturation levels at both these sites. And a similar pattern of high carbon density was found below the sedge and the rush area, below the communities that had predominantly sedge and rushes, and the areas that had high bulk density, so that had high soil bulk density in their soils. So it was observed that soil bulk density was a contributing factor for higher soil carbon density values at both wetlands. And willow swamp forest, and sorry, I'll switch to another slide. And once I had these soil density values, I determined the total carbon stock values at both wetlands, which showed an increase with the overall soil depth. And I determined the total soil carbon value by summing up these three, the stock values at the three layers. And the highest soil carbon stock value was consistently observed for sedge species across all three layers for both wetlands. So what I found that Travis, being an older wetland compared to Sparks, was storing roughly 41,627.3 ton of carbon in its soils up to 90 centimeter depth. And Sparks wetland was storing up to 3,358 tons of carbon in up to 90 centimeter depth. So by this, one observation that came from these values was that Sparks has, although it is around 5 years old, it has still started the process of sequestering carbon in its soil. And Travis is already acting as a carbon sink within its soil. And in freshwater wetlands, it's a known trend that soil carbon stock value increases with soil depth. So this value is only up to 90 centimeter. And based on the literature, based on the studies from scientific literature, I can confidently say that in the deeper levels of in the deeper soil depth levels, there's going to be more carbon as compared to the ones that we found at the superficial levels. This is true for both the wetlands. So one part of my project was understanding the soil carbon storage. And another aspect is to look at the linkages between above and below ground carbon storage at both these wetlands. So what I mean by that is that I am broadly studying the plant communities that are occurring at these sites, which there is a gradient or there is a particular structure that was commonly observed when I was recording the plant assemblages at both the wetlands. So it commonly follows, it goes from grasses to shrubs to native forest species. So I'm looking at the broad level plant community structure and its influence on carbon storage at both the wetlands. And I'm also looking at the plant assemblages along the established transects in my project. So what I mean is that I'm recording species that are occurring along a particular cross section, and I'm looking at the above ground carbon profile of these plant species using the formulas that I've determined from literature. And I'm simultaneously looking at the correlations between above ground carbon and the below ground carbon, and trying to see whether there is any correlation between the two for the wetland. So what I found from up till now, what I have found is that the vegetation located on the soil surface has a huge impact on the composition of the organic matter, which in turn is responsible for binding carbon compounds in the soil environment. And one of the reasons for this is the root system of these species, which penetrates deep into the lower layers of soil and then breaks down the soil organic matter. And the roots decompose on the surface of the litter, and this is where the organic matter is forming. So large amounts of carbon are usually in the wetland. The large amounts of carbon are usually characterized by a well-developed root system, production of large amounts of biomass, and efficient water management. So because these, especially Carex, with its root system, with its adventitious root system, it has a high water storage, water holding capacity. So these wetland species are able to withstand higher waterlogged conditions, which slows down which delays the activity of soil microorganisms, which are responsible for decomposing these the organic litter, which is found, which is the dead organic litter, which is found within the first 30 centimeter layers of the soil. And when this activity is delayed, that leads to larger amounts of carbon accumulation. So the vegetation has a very important role in determining the quality of the organic matter, the input of the organic matter, and the activity of soil microorganisms in those areas. So I'm looking at the different types of root systems of the species that I have identified at both of these wetlands, and for this I am dependent on the published studies in New Zealand to see the root structure and to come up with an understanding of why certain areas in the wetland have a higher carbon storage compared to other areas. So I believe that the research implication for this project will benefit both landscape architects and the scientific community, in a sense that the research will have, although research will have implications for both new and restored freshwater wetlands in Christchurch that could improve carbon storage in the wetland soils and in their above and below ground biomass. It would also help in revealing these patterns of plant-soil interactions at both of these wetlands, which could then be open for further investigation, that how are certain plant communities or certain plant assemblages influencing the soil the activity of soil microbes, which are responsible for releasing carbon into the atmosphere. So it will create that a database or patterns from which such kind of investigations can be taken further. Second is the larger goal of this project is to determine ways through which landscape architecture as a discipline contributes towards climate action through design of urban wetland ecosystems. And also I want to come up with like these revelatory patterns which explain the influence of plant diversity on plant, soil, and carbon interactions within the domain of freshwater wetlands as an ecosystem. Thank you so much for listening to me. Thank you.
Thanks, Shachi. Over to you, Charlotte.
Hi everyone, I'm Charlotte Calder. So my master's was focusing on managing carbon emissions through riparian design plantings on an Otago farm in Aotearoa. So my supervisor was Dr. Gill Lawson and my advisor was Di Lucas. Just going through a bit where my site is located. So my site is Lauder Station. It is located in the Menuhirikea Valley in central Otago, South Island, New Zealand. The main land use within the valley is farming, mainly sheep and beef with a little bit of dairy grazing as well. It has highly productive flat paddocks within the valley with a lot of irrigation being implemented. It also has a large area of the valley floor being included in the new stock exclusion zone. Just a bit of history on the valley as well. So about 20 million years ago, it was a subtropical wetland known as Lake Menuhirikea. Within this lake, there was a lot of different species of plants and animals with crocodiles, flamingos even, and then also squawkzilla, the 1 metre tall parrot. So fossils have been found throughout the valley of those ancient creatures. And then going forward in time around the 1860s, after colonisation and after Polynesians had gone through and hunting moa and burnt most of the native forest that was in the valley, Europeans came in and started gold mining with a lot of old sites, transforming the landscape into completely different looking landscapes. So a bit about Lauder Station. It was first recorded to be farmed in the 1850s. The property size now is just over 1,224 hectares. So the altitude ranges from 440 metres to 1,550 metres. The annual rainfall is quite low, between 650 to 700 mils a year. Current stock numbers are 4,000 sheep, 150 cattle and 4 bulls. The farm did go through the process of tenure review, where 75% of the farm was gifted back to the Crown. So then the remaining land became freehold from being leasehold. So with that conversion, loss of land, some intensification matters had to be made. So there is now 125 hectares of spray irrigations on the lower areas of the farm. Just a bit of background of sort of the wider scope of the project. So looking at the sort of Paris agreement that was made in 2015, and then New Zealand sort of committing to the Zero Carbon Act as well, and sort of how farmers can sort of reduce their emissions, and what are the future possibilities for them. So getting the farmers to know their greenhouse gas emission numbers, and then different options in reducing those emissions, and sort of making changes to the farming system. So sort of my gap in the research was sort of how can landscape architects help farmers design riparian plantings that will store the carbon emissions, so inset the farm's emissions to meet the new government regulations. So my sort of questions were, how have the farms in the Manuherikia Valley and Central Otago changed the patterns of production and carbon emissions, potentially in response to the climate environmental changes over the past 10 years, and then going down in scale, how has the family-owned farm changed its patterns of production in relation to productivity requirements and carbon emissions, and then going down to even a smaller scale at the paddock sort of level, what farm level changes are needed to shift from crop to creek to better manage carbon emissions as well. And interweaved within my research, I was looking at the landscape ecology theory from Foreman, so looking at the different patches within the landscape and the matrices, and then the corridors, mainly of the waterway corridor that travels through the farm, the edges and boundaries, and then the land transformation from going through the land tenure process and sort of those transformations for the farm. So my methods of my research was looking sort of mainly at the mapping of the spatial data that was available, then looking at the literature calculations of existing carbon emissions for sheep and beef farm, and then the calculations for the storage as well. Then using software platforms that are available for farmers to use to calculate the farm's carbon emissions. Then going on from there to work out a riparian planting design that will inset the farm's emissions and calculating the total carbon stored within that design. And then finally coming out to see how much of that planting design would need to be planted to inset all of the farm's greenhouse gas emissions. So I'm just going to show you a couple of my results of the different mapping that I did. So this is mainly looking at the valley scale, the land types, water supply, and sort of water races that run through the valley. So there is 3 different land types, so the upper mountain slopes, the lower mountain slopes, and the minor valley floors with colluvial side slopes. The highest percentage is the minor valley floors, with the most productive land for farming found in this area. You've got the sort of 2 main waterways that travel through the valley. Most of these 2 waterways are supplying a lot of the water for irrigation for farms further down the valley as well, and in this area as well with the Manuherikia Valley that comes out of the Falls Dam, so it's in storage area, and then the Dunstan Creek, and then there is a waterway that flows from the top of Lauder Station, which is outlined in the red, out the bottom of Lauder Station and into Dunstan Creek, which is Bullshed Creek. This map here is just showing the sort of change in irrigation for the valley. So the lighter areas is irrigated areas in 2017, and then just 3 years later, the darker orange is irrigated areas in 2020. So there has been a large increase in irrigation just with drier conditions in the summer seasons. Farmers are just finding that there's a lot more productivity with an increase in irrigation across their farms. From there, I mapped the vegetation types and then used some literature to sort of work out for each vegetation type how much carbon was stored within that area. So my main findings were that the vegetation type that had the largest carbon storage was the grassland with Matagari, and also the short sort of snow tussock sort of grasslands, which is found in the higher country, with the improved pasture and unimproved pasture having the least amount of carbon storage for all the vegetation types. Going down in scale, looking at Lauder Station, so most of the station is in the lower mountain slopes, which is between 500 metres and 1,000 metres, with a small section at the lower end of the station being in the minor valley floors. So that is where most of the productive paddocks are, with the irrigation as well. And then you can see there the Watershed Creek running from the top of the station out the bottom and joining up with Dunstan Creek. The station also has 2 storage ponds for irrigation. So there's an intake from Watershed Creek, and then there's also an intake from Donald Stewart Creek, which is over the next gully from the farm. So that travels through the neighbouring property into a storage pond on Lauder Station. The irrigation hadn't changed over the 3-year period, with just the main areas being down on the lower areas of the station. But the vegetation cover, there was a lot of different types found within the station, with there a large amount of unimproved pasture, so sort of that more native grasses and just untouched sort of grassland on the farm, so that wasn't storing as much carbon compared to the mixed Indigenous scrub that was found around Watershed Creek, as well as the Manuka and Kanuka, as well as the tussock grassland. And there's also on the farm, from the land tenure process, an ecological covenant within one of the hill blocks. So this area is not allowed to be grazed by any cattle or to be sprayed. So there has been a large amount of natural regeneration of native species, especially scrub, happening in that area. And then moving on to sort of the calculations I did through Overseer and in the literature. So Overseer came out with 1,722.1 tonnes per year of carbon, greenhouse gas emissions. And then from the literature, there was quite a difference, with 3,952 tonnes of greenhouse gases per year. And then combining all the vegetation types from the literature, it came out as 14,220,000 tonnes of carbon stored per year. So the vegetation types were storing the carbon, but wasn't recognised through the EST trading scheme. Then looking down at the paddock scale, so this is one of the paddocks on the sort of irrigated flats of the station that runs along Lauder Station Road. This paddock has no irrigation. There is a natural spring within the paddock that then flows out to Watershed Creek. The sort of change that was seen in the sort of riparian corridor was that there was a lot of exotic willow species, and over time there had been a patch cleared next bordering the paddock that is outlined in red. There was sort of cutty grass and spike rushes were sort of the only native plants that were found in the riparian corridor, but it was mixed in with sort of cutty grass, couch grass and thistles that were causing had no biodiversity, low biodiversity within the riparian corridor, and wasn't doing much in shading the waterway as well. So then I selected a 1 to 200 riparian vegetation design site from there. This is sort of visualization of sort of what the proposed site will hopefully look like after 15 years. So it's just the before and after. This here is sort of the planting design I did. So I split it into sort of the lower bank areas where the wetter areas were, having a wee dryland wetland. So in the wetter months, there'd be a wetland, but in the summer months it'd be dry, pretty dry. And then moving up from there, the middle bank, and then the upper bank as well, with a sort of larger native species growing up there, and more of the sedges and rushes growing down in the lower banks. From that design, I then, using literature and making quite a few assumptions, I worked out the carbon sequestration of each species, and then the total from each species in that design area. So overall, the total was 10,613.8 kgs of carbon per hectare per year. So the only certain number I had without having to do any calculations myself from the literature was the Coprosma robusta at 2.6 kgs of carbon per hectare per year. From that total carbon sequestration, I then worked out how much planting was needed to sequester the emissions from the shed paddock, which was 1.11 hectares of riparian planting needed. I then from there also calculated the total area using that riparian planting as like a template, that there would need to be 60 hectares to inset the carbon emissions from Lauder Station. So my challenges that I found in the research was that there was a limited literature on the carbon storage of the native plant species in New Zealand, so actually like a definite number instead of me having to use the equations for the process. Also the limited literature calculations for high country sheep and beef farms. There wasn't sort of a total emissions for sheep and beef farms within the literature. Also just with how rural the site is, the limited clear imagery for my sort of analysis and the mapping as well. And that's it. Thank you.
Thanks so much, Charlotte. There's some time now for questions if anybody would like to maybe raise their hand so we can see who'd like to